Welcome to the 2020 Climate Science REU Final Symposium. I'm joined by my co-director, Greg Jenkins, and we've got a lot of great presentations lined up. I know both of us are looking forward to hearing all you've learned and looking forward to learning from all of you over these 2 sessions that we have planned. 2 70-minute sessions, 7 talks each on a variety of topics in climate science. So welcome to the students, 14 students we have in the program. Welcome to all of the mentors. I see many have signed in. We've got about 40 participants now. And welcome also to any guests that might be joining us from Penn State, some of our collaborators and colleagues. Welcome to any family members and friends of the students. Really happy to have you. This is one of the nice sort of silver linings of the virtual program that we're having. It does actually make it more open and accessible to a wider audience. We have never had an online component before. We've never live streamed, but maybe we'll do that. Hopefully we'll be back in person again next summer, but we'll try to include a online component so that we could have a family and friends and others join us. So really thrilled to have you. A few thank yous are in order here. My Brooklyn accent sneaking out there. I want to thank the Department of Meteorology and Atmospheric Science. They host the REU program. So I want to put a particular thanks out to my department head, Dave Sensrud, who's been very supportive of the program in multiple ways. And all the wonderful staff we have in the Department of Meteorology that have helped us, help the students get paid, help them get their accounts, things like that. Jen Renault, Christy Weller, and Lynn Persing in particular. I'd also like to thank Chris Turnbull. He's really made the work of Greg and I a lot easier this summer by organizing a lot of the symposia, helping out with computational support, and just helping out whenever we needed help. He's really been wonderful. I'd also like to thank the sister program that we have here at Penn State, the Project Drawdown REU, and we've had several joint programs with them, which have been really, really great. And they have their symposium tomorrow at 10, and I encourage you to attend that. So without further ado, let's get started. We have a series of 7 talks in this first session. Speakers will have about 7 to 8 minutes to give their presentation. I'll give a 1-minute warning at around 7 minutes, and then I'll do that in the chat box, and then I might cut you off if you go on too long. But we'd like to leave about 2 to 3 minutes for Q&A and changeover. So let's get started with our first presentation by Malaz Alhirsh, who is an Earth and Environmental Science major at Brooklyn College, and he's going to be speaking about assessing resilience to climate change in coastal Alaskan regions. So Malaz, the floor is yours, and Chris will be sharing his screen. We'll allow you to share your screen.
Okay. Well, thanks, Professor Najar, for introducing us. Just waiting for the permission to share. Okay. All right, so my project, as Professor said, assessing resilience to climate change in coastal Alaskan regions. And research has shown Alaska has warmed twice as fast as the global average during the past half century, and we all know it's due to climate change. And here's just the mean annual temperature in Celsius from the year 2009, just to show the layout of temperatures in the state of Alaska, which north is the coldest, south is the warmest. And climate change has been hitting the coastal regions pretty hard. Some researchers say that the coastal regions are the front lines of global climate change. So we chose to study three different coastal regions in Alaska. First one is Dillingham in the south, Scammon Bay in the west, and Wainwright in the far north. And we chose these communities because they have different climatology and fall on a latitude gradient. And now before we talk about how the climate changes or temperature increasing is affecting these coastal regions, first we have to understand their local temperatures and how are they changing locally. And here's the first one. I'm going to start with Dillingham. And just a brief background on how we got our information is we took the climate data from the fifth report of the IPCC and downscaled it, producing three different future projections, or the RCPs. The RCPs are, they just stand for representative concentration pathways, which they measure the concentration of greenhouse gases in certain range. The ranges are 4.5, 6.0, and 8.5 watts per square meter, just to measure these gases. And as we can see from these plots, that the baseline is 1961 to 1990. So we can compare and see how the temperatures are increasing, and we can clearly see that in 2020, 24, and 2060, temperatures will be increasing drastically. And here on the bottom right is just those numbers of degrees for each month. But as we can see, in the summer months, there's not much change to close to each other with the RCPs. However, if we looked at the winter months, we can see that temperature change is happening happily. And in 2060, that's the most change we can see in Dillingham, as in go up to 5.9 degrees of increase. These are some huge numbers. Now going on to Scammon Bay, temperatures in these winter months increases even more. It can go up to 8.6 degrees. Now remember, these are just trend lines. So these are not exact numbers, just giving us a projection of what might happen. These are the possibilities of these happening. And then going to Wainwright, again, 2060, we see these huge changes in degrees and can lead up to 13.3 degrees increase. And the ranges increase. So we will have November, December, from November to pretty much April. So what does these temperature increases mean for these local regions? Now here is just a representation of what's going on. And the first effect will be the wildfires. So wildfires are increasing in Alaska. The Alaskan Interagency Fire Management Organization changed the start date from May 1st to April 1st. So that's a month before. That's due to the increase of wildfires. And wildfires, the next thing will happen is the permafrost thaw. So because there's high temperature and high precipitation, there's more rainfall, and rainfall can affect the ice coverage and snow coverage. Now these are important because the snow and the ice reflect solar energy, and without this reflection, the ground will absorb this energy and help speed up the process of permafrost thaw. Permafrost thaw is very important because when it's frozen, it can be harder than concrete, and the Alaskan infrastructure is built on this permafrost thaw, and if it's thawing, these infrastructure will be vulnerable. And the next thing, due to earlier melt and snow, there will be more rainfall and evaporation, and that will lead to more storms, and that will cause flooding and erosion. And that's very significant when you're talking about coastal regions. And these three effects can also change or affect the vegetation process and as well the growing season. So that can affect the food source for animals living in the area or even migrating. So we do see migration patterns changing to the climate change. And adding all these effects and damages that's going on because of climate change, scientists have researched that there's process gonna happen called climate migration, which is pretty much communities getting relocated because of these global effects changes. Now going to the economic side, we can talk about how these projection costs. So how much will it cost for the state of Alaska to repair these costs and keeping their community safe. And one of the papers suggested from 2015 to 2099 will cost, without doing anything, just keeping the course, it's going to cost $4.2 billion to $5.5 billion just to cover the costs. And there are many variables in this, so they might go up. However, these are numbers they have had. But if we've lessened our greenhouse gases concentration and there's some adaptation to it, we can lower the cost of these damages. So in conclusion, these temperatures are affecting many aspects in these coastal regions, from wildfires, permafrost, flooding, erosion, damage to local infrastructure, animal migration, and climate migrations. And that will be it. Any questions?
Thanks, Malaz. Does anyone have any questions? We'll just take them sort of live. So if you do, just unmute yourself. I think you should be able to, and fire away.
I have a question.
Yeah.
Through your research, were you kind of surprised at some of the results that you came up with? Was there anything like interesting that you saw when you were looking at it?
Actually, yeah. So when I got the results of my models, I was surprised how temperature change is just changing in the winter months rather than the summer. So summer, we didn't see that much difference. However, it can be dry. So there are some drought situations that's going on in Alaska, but effects of winter, the effects of climate change in winter really surprised me, and how far the range can be. So the increase in wildfires, even the permafrost, I didn't know I didn't have that much knowledge that permafrost can be that much damaging. But when we talk about infrastructure, I mean everything: infrastructure, pipelines, houses, roads, airports. And in Alaska, it's like spotty region, so you can't really, if you want to go to one place to another in certain areas, so you have to go by plane. So these airports are very, very important in these regions.
Anyone else?
I have a question. You may have said this, but in the different RCP scenarios, roughly how much does the CO2 concentration vary?
Well, going back to my computer froze at this time. Right, there we go. So going back, so let's say Wainwright, you can see this concentration is just changing within the lines, and you have these table right here, just to show, so the increase will show you the different concentration that we'll have. So the way they did it is they just looked at the concentration they have in the past and present, and then just projected it from this base our output of our greenhouse, and just they did math and numbers and projected it to see how much it is in the future.
Thank you.
Great. Thanks, Malaz. We're going to go on to our next presentation by Gabrielle Linscott. She is from Hobart and William Smith Colleges and is majoring in geoscience and Spanish with a concentration in atmospheric science. And her presentation is entitled Uneven Experiences of Urban Flooding, a Spatial Analysis of Social Vulnerability, Historical Segregation, and Floods. Gabby?
Thank you. Not sure if I'm okay. I'm on this share screen. Let's see. Okay. So hi, everyone. Like Ray said, my name is Gabrielle Linscott. I've been working with Andrea Wishworth and Brian King over the summer in the Department of Geography. And I'm just going to tell you a bit about my project, Uneven Experiences of Urban Flooding, the 2010 Nashville Flood. Okay. So essentially, over the course of the summer, I have designed my own research project, and I'm in the process of executing it right now. So a little bit of context. With increased global warming, we'll see an increase in the intensity of precipitation and flooding, especially in the southeastern United States. So when we see increased flooding, what are we talking about in terms of health impacts? We'll see injuries, death, mental illness, post-flood disease spread, power outages that can lead to carbon monoxide poisoning, gastrointestinal diseases, along with a plethora of other things. So it's really important to know who is this impacting the most. Previously, there have been few studies on the flood impacts in the United States. So I'm really looking at what is the composition of these vulnerable populations. And you can see here on your right, this is a map of the redlining in Nashville. And although redlining has been banned for a very long time, the systemic disadvantages it enforced on minority populations persists in many US cities today. So that's kind of the frame at which I'm looking at my research. So a bit of the event overview. It was 2 days, a 48-hour period in August 2010. The flood caused over $2 billion of damage, and there were 26 fatalities related to the flood. And you can see here on your left, this is from the Nashville downtown core, obviously after the flooding, but you see a lot of standing water. And right here, you can see a car almost completely submerged. So essentially, there was 2 low and high pressure systems over the United States, which led to a surge in moisture from the Gulf Coast of Mexico. This was later classified as an atmospheric river. So the atmospheric river interacted with a stationary front, resulting in the development of severe thunderstorms that caused flooding. And this is just your 48-hour rainfall totals from the Community Collaborative Rain, Hail, and Snow Network, known as COCORAS. And you can see in Nashville here, with these contours, the totals in Nashville range from 14 inches to 20 inches. So in 48 hours, it's a lot of rain to fall in one area. This is an aerial look from above. This is the Cumberland River kind of meandering through, and your urban core is right around here. So this muddy color extending outwards from where the river normally is. From this altitude just shows the extent of this flood. And overlapping that with our redlining districts, this is really framing my question of, okay, so I know this history of historical segregation. Are these populations still there? Who is this flooding impacting? So our methodologies are adapted from a tradition of social vulnerability and hazards methodologies from Cutter 2003 and Hung 2016. On your right, this is a map of Davidson County in Tennessee, and you can see all these checked boxes are Nashville. So this is the area at which I'm pulling census tracts for. So using American Community Survey variables, which are very similar to census variables, and looking at specifically ones in Nashville, we perform a principal component analysis in RStudio to figure out which variables from the ACS are most important when considering who is impacted. And I can tell you about PCA, but to save time, I'm gonna skim over it for now. So using those PCA results to define new principal components, new variables we're looking at, we'll look at how that goes. So for our preliminary results, you can see here, this is the number of the principal component. And then the total number, the total percentage of the variance that it accounts for. So within our first 8 principal components, they account for 80%, almost 80% of the total variance of our data set. So now our next question is, okay, what comprises each principal component? And these are some of our preliminary results. So for principal component 1, which accounts for 28% of the variance, it's a household that is the house that is owned by the owner, occupied by the owner, sorry. Then from there, it's people below the poverty line with a disability, people of 2 or more races, including Hispanic or Latinx, women, particularly Black women, then followed by Hispanic and Latinx, and then white women. People with a disability above the poverty line, American Indians and Alaskan Natives, and then people of 2 or more races, not including Hispanic or Latinx. So our next steps going forward in our analysis will be to map each of these 8 principal components onto the census block groups that we pulled from Nashville to see how these variables are spatially distributed. Then we'll create shapefiles from our flood imagery and finally overlay all of our data according to this schematic that I've made. And that is about it. Thank you. I'll take any questions.
Thanks very much, Gabby. Anybody have any questions for Gabby about her presentation?
Hey, Gabby, this is a great presentation. My question is, do you know, in the 10 years since this happened, has the city of Nashville done anything to prevent some terrible flood that disproportionately impacts these communities, or is it largely the same situation? Or are they just as vulnerable?
Yeah, so I haven't looked at how these populations have moved since that, since 2010. So I'm not sure. I assume that they're still in the floodplain. But with this event, there was largely a sense that the population in Nashville was unwarned despite a lot of warnings being sent out by the National Weather Service. So they've worked a lot with increasing the science communication in that region and including meteorologists in their emergency management centers during extreme events.
Hi, Gabby. I'm interested as to how much it's expected to change the extremes in the next 50 years. Was there much discussion of that and how that would map on to the types of changes that you might be expecting in that area?
Yeah, so when I was doing my literature review, I was having a really hard time actually finding studies about flooding in the United States, with exception for the work that Dr. Shepard has done in the Deep South. So a lot was done in Bangladesh, less so in the United States. So it's definitely an expanding body of literature, but I was unable to find specific 50-year projections for this region that I'm doing. There was definitely a lot of calls for further research.
Thank you.
Anyone else?
Yeah, I had a quick question. Is there a reason to pick Nashville in particular? Is this an area that's kind of prototypical of other urban areas around the country? You might have said that in the beginning, I might have missed it, but anyway.
No, I did not say that. So I wanted to look at a city that had a diverse population that was also within a date range that was easy to find data for. So this just happened to be a pretty extreme event where a lot was documented from it. There have been reports put out by the NWS, so it was easier to find information about it. And since Nashville is a pretty diverse city, I thought it would be easier. And since it was such a large event spread out over 2 states, the rain fell on a lot of people, but how it impacted different populations was really the question I was interested in. So it was a large scale storm, diverse population, lots of data. Yeah.
Great, thanks, Gabby. We'll move on and sort of continue the theme of water. And the next presentation will be by Starlivia Kaska. And she is an environmental hydrology and water resources major at the University of Arizona, working with Alfonso Mejia. And her presentation is called Finding a Solution to the United States Water Use Data Deficit. Floor is yours, Starlivia.
Can you see my screen?
Yes.
Okay, thank you. Okay, good afternoon. My name is Starlivia Kaska, and like Ray mentioned, I'm under Dr. Alfonso Mejia. I work closely with graduate students Natalie and Fiorella. They're all under the Civil and Environmental Engineering program there at Penn State. And as you mentioned, the title of my project is trying to find a solution to a water use data deficit here in the United States. So let me begin by saying it may kind of surprise people to know that the United States has a lack of water use data in the United States. And it comes as a surprise because sometimes we think of the United States as this big old giant who knows everything, right? But what we see as researchers is that water use data is often vague and there's a lot of missing values. And in order to bypass these issues, researchers often substitute water use data by plugging in Canadian water use data or finding different ways of figuring out how much water different sectors are using. such as using production data and like employee data in order to find exact values of water use in certain subsectors. So all of this comes from a lack of data that the United States has. And to begin proper water resources management to deal with climate change, we need to find out how much water we are using here in the United States. So our research kind of works with trying to figure out how much data, or working with data to find out how much water is being used in the United States. So our research methods start with data acquisition, trying to find out how much water we're using. We download a lot of data from the USGS as well as the Canadian Public Data website. And then we aggregate all of this information, which kind of just means organizing all of the numbers that we get, trying to figure out how we want to use this data at a county level, state or national level. So I worked a lot with Excel spreadsheets, organizing all of the numbers, trying to figure out which numbers that we needed. And then we finally did a data comparison with all of the data that we collected for the United States and Canada. And we did 3 comparisons between all of these data that we collected. So the first comparison was USGS versus Canada. The second one was USGS versus US Army Corps of Engineers, which is the data that we have in our lab. Then we finally did a final comparison between USGS and USDA. And here are the results of all of the data acquisition and aggregation that we did. The first one is Canadian data versus US Army Corps of Engineers data sets. So this first graph here shows all of the sectors that we did comparisons between, and this is water use in gallons per employee per day. You can see that there's 4 major ones that are outliers. There are huge differences between the United States and Canada. The green is Canada, the grayer color is the United States Army Corps of Engineers data set. When removing these 4 major ones that kind of threw off our scale here, we come up with a better bar graph here when we remove paper, petroleum, coal, and chemical and primary metal from here. And there's all of these are just subsectors letting you know where the water is coming from. So this graph is after we've removed these 4 here. You can see it's kind of like at a better scale, but still we see a lot of differences between Canada and the United States Army Corps of Engineers data. And here's just a linear correlation. We find a linear correlation of 0.52, meaning there isn't that much similarity between the 2 data sets. Here is USGS versus US Army Corps of Engineers, and here is just us at a state level domestic water use. For USGS here, and then this second map is a difference between the 2. So showing here yellow towards the middle kind of just shows us that the data between the 2 are pretty similar. So we're pretty good here in the middle of the United States. And the red value just shows that USGS is estimating more water use than the US Army Corps of Engineers. Green is at the other end of the scale, which is showing that USGS is estimating less water than the US Army Corps of Engineers. And linear correlation between USGS and the US Army Corps of Engineers is 0.98, showing that there's a lot of similarity between the data sets. And here is just another water use map, but this one is at a county level, just letting you know that we did work at county level, trying to figure out water use in each county. Then here is our second comparison, which is USGS versus US Army Corps of Engineers. industrial water use at a state level. This is the first comparison, I'm sorry. But this is industrial water use. We can see that there's major differences here. Linear correlation of 0.4, letting us know that the two data sets for industrial water use are pretty different. And then here is our other comparison, which is USGS versus USDA in crop irrigation. Here we can see missing values here in the USGS data for water use for these states here. USDA has a lot more water use data for from their data set. Here are the differences here again. Red meaning USGS is estimating higher water use here than USDA. USGS here is underestimating water use compared to USDA. Linear correlation between the two is 0.89. So some similarities here if we disregard the missing values from USGS. So take-home messages, conclusion to my presentation and to our research is that Canadian data isn't representative of the United States. It depends on what subsectors you're going to use and which ones you're going to compare, as we saw in the bar graph. The data between USGS and U.S. Army Corps of Engineers is a better correlation, but then I'd like to let you guys know that USGS has a macro scale sort of way of letting us know how much water use we're using. They have 7 sectors, whereas U.S. Army Corps of Engineers has a number of subsectors. It's more detailed, but it's very old data. And the United States needs better water use data for the United States. So in conclusion, we saw that there seems to be potential to combine the data sets to produce better water use estimates. That's the end of my presentation. Do you have any questions?
Thanks, Starlivia. Questions?
I have a question. So with the 2 measurement groups that or the data sets that you were comparing, was the method of collecting the data different between the 2 of them?
No, we went ahead and collected data from public sources for all of the comparisons that we did. So method wasn't changed at all for any of them when collecting the data. We just downloaded most of the data from public places.
I also have a question. So if I understand correctly, sounds like different data resources, their data were connected at different times. Am I correct? So some data are newer, some data are older. So the differences perhaps also include like the difference in the actual water usage across different years.
Yes. And then just to mention, like the year we were trying to focus on 2015, sometimes there wasn't data available for 2015, depending on where you looked. So we had to use the most recent water use data that was available. Sometimes it was 2013. So yeah, it depends. If I didn't really understand your question. Sorry.
Well, we better move on. Some of you have already taken advantage of the chat box. I forgot to mention that, but you could continue the conversation in the chat room. So feel free to use that to follow up with any other questions you might have for the speakers. So our next presentation is also a hydrology presentation, and it's by Juan-Pablo Speer. He's a physics major and math major at the University of Alabama at Birmingham, and his presentation is entitled Investigating Concentrations of Dissolved Silica in Watersheds Using XGBoost. Juan-Pablo.
Thanks, Ray. Want to make sure you guys can see the title slide?
Yep.
Okay.
Good.
Well, hello everyone. My name is Juan-Pablo Speer, and I, along with Kayal Sadayapin, Wei Ji, and Dr. Li Li, have been investigating the concentrations of dissolved silica in watersheds using an XGBoost machine learning algorithm. So the primary mode of transportation for dissolved silicon is via watersheds. Watersheds are better known as water catchments or river basins, and they are basically pieces of land that topographically direct all water towards a local stream and eventually into larger bodies of water. Each watershed is unique and therefore provides unique pathways for the water to flow through. So depending on the watershed, the water may have participated in several biogeochemical processes before being discharged, used by vegetation, or simply evaporated. So water quality obviously is of utmost importance to humans and all other organisms. And the only way to maintain and improve water quality is by understanding and being able to predict hydrobiogeochemical events. This is especially important right now as increased climate activity and human activity could lead to excessive contaminant output in aquatic systems. And this could be a catalyst for waterborne diseases or ecosystem collapse. On the right here, you can see an algal bloom in Florida that was caused by the damming of a river. So you're probably wondering, why should we specifically focus on dissolved silicon? Dissolved silicon is the main source of nutrition for the phytoplankton groups that are responsible for producing half of the oxygen in our atmosphere and are the base of virtually every oceanic food web. They also function as algal regulators, thereby increasing water quality. And silicon enters bodies of water via silicate mineral weathering, volcanic activity, or the water may come in contact with biogenic silica in the form of the shells of microfossils or silica generating vegetation. So the data that we used for this work came from the National Center for Atmospheric Research under the CAMELS data set. And the first thing that we wanted to do with this data set was draw relationships between the mean concentration of dissolved silicon, I'll be calling it DSI from now on just for time's sake, and the relationships between DSI and environmental variables. Here they're called predictors. So here on the right, you see a correlation matrix, and I show the 7 predictors that showed the highest correlation with mean DSI. So on the top row, you can see those correlations. They're relatively high, but it is also important to note the correlations that predictors have with one another. So for example, precipitation mean, the second row, and runoff ratio, the fourth column, have a pretty strong correlation with a coefficient of 0.65. And this could be a sign that there's redundant information in one of these predictors. And that is in fact the case, as precipitation mean is used to calculate runoff ratio. So on the left, I've listed the predictors that I believe to be non-redundant based on the correlation coefficients that you see on the right. And here I've plotted those non-redundant predictors. On the top left, you can see the relationship between precipitation mean and mean DSI concentration. And initially I thought that this was a strange relationship, as increased precipitation I thought would lead to increased weathering and therefore increased concentration of DSI. But this is actually very normal for weathering samples that you see in nature. On the bottom left is the leaf area index difference against the DSI concentration. And what this plot is basically saying is that there's higher DSI concentration in catchments with stable leaf area throughout the year. The top right shows a relationship between DSI concentration and catchment area. So this made a lot of sense to me, as increased catchment area. I thought that this would lead to an increased chance of silicate minerals in the catchment area, and therefore more dissolved particulate. And on the bottom right is a spatial relationship between longitude and mean DSI. But this is more aptly seen in this plot, which not only shows the location of our catchment sites, but also they're differentiated by longitude and mean dissolved silicon concentration. So if you live in the center of the country, there is a greater likelihood that you have a catchment near you with relatively high dissolved silicon concentrations. So scatter plots are useful for seeing relationships between two predictors, but we wanted to create a model that took into consideration all of our predictors. And this is where the XGBoost machine learning algorithm comes in. And the XGBoost library basically makes use of two ideas, which are decision trees and gradient boosting. So the first thing that we had to do with our data was to split it into fractions of 80% and 20%, 80% being training data and the other 20% being testing data. And what the XGBoost algorithm does is it takes the 80% of the training data and using yes or no questions, it organizes them into the classification and regression trees that you see on your left. And it organizes them until there is a row of subgroups. They're also called leaves. And so when everything is organized, you take the average mean C of each subgroup, and then you organize the training data, or sorry, the testing data using the exact same tree. And in whichever subgroup the testing data point falls into, that mean C is attributed to that testing data. And then we run an R-squared test on it to see basically how well the decision tree predicted the testing data. And the gradient boosting process that XGBoost makes use of is basically sequentially adding models onto weaker models in order to improve, in our case, we were improving root mean square error. So if, for example, if one of the leaves had a high error, the algorithm would include more branches into that leaf to try and organize further and get better results. So here is the best model that we could get with our data for dissolved silicon. And this had a success rate of 55.7%. And though we can't see the actual tree, we can extract data from the tree. And on the left, you can see an importance plot that shows the predictors that mostly improved testing performance. And these are runoff mean, elevation mean, and green vegetation fraction difference. And this was a bit kind of disappointing for us because we expected there to be high correlations between mean C and the top three variables. And as you can see on the right, the R coefficients aren't very impressive. So we predict that this is because we have a lot of redundant information in this model. So for example, precipitation mean, low precipitation frequency, low precipitation duration, and P seasonality. These are all hydrological predictors, and they may contain redundant information. So in the future, we'd like to remove these predictors that carry this redundant information. And using a more successful model, we could derive actual reactive transport models from the XGBoost results. And from there, we can explore temporal patterns of individual watersheds, verifying DSI concentration. Thank you.
Thanks, Juan-Pablo. We have time for maybe one question or two quick ones.
Yeah, I have a question.
Okay.
Hi, Juan-Pablo, thanks so much for the great presentation. I was wondering, on removing the correlated predictors, would your strategy more be looking into the literature about that kind of thing and seeing which ones make most sense in terms of a theoretical background? Or does XGBoost offer some kind of analytical process for removing those predictors?
From what I know about XGBoost, I'm not sure if there's that kind of functionality, but we've already actually kind of talked about this as a group. We have a few other members trying to do the same thing with their predictors, and we've already decided kind of which predictors we're going to take out. So hopefully that will yield better results, but if not, we'll probably just keep guessing and checking. But hopefully there'll be some literature on it that we can find.
Great, thanks so much.
Yeah, thank you.
Thanks, Juan-Pablo. Very interesting stuff. I'd like to follow up with you on some things there that I'm interested in. We better move on. We're going to have a couple of carbon dioxide talks. And the first one is by Eli Vogel, who is a physics major at the University of Maryland, Baltimore County. And his presentation is entitled Using Eddy Covariance to Measure COVID-19's Effects on CO2 Emissions in Indianapolis, Indiana. Eli?
Awesome. All right, everyone can see that?
Yes.
Okay, cool. So hello everyone. This is my project on using eddy covariance to measure COVID-19's impacts on human emissions in Indianapolis. Thank you so much to my mentor, Dr. Davis, my other co-authors, program directors, Dr. Najar and Dr. Jenkins, and the NSF making this possible. In order to know if humans' efforts to curb climate change are effective, it's important that we have the ability to measure how much greenhouse gas we're actually producing. So COVID-19 is actually a good chance to test our ability to monitor human emissions, since we know for a fact human activity is down during the lockdowns. So the focus of this project is an eddy covariance tower in the western half of Indianapolis, Indiana. It directly measures CO2 flux within this red circle right here, which has a radius of about 400 meters and has suburbs to the west and a highway to the east. The project has two goals, the first of which is to determine if the tower's observations are similar to the traffic patterns on the nearby highway when wind is blowing from the east. The second goal is to quantify how emissions change during the city's COVID-19 lockdown and compare those changes to changes in traffic. The answer to these questions will determine if the eddy covariance tower can accurately measure the emissions from a specific source and tell us if that source is decreasing output. One of the biggest difficulties in measuring emissions is the process of figuring out how much of it is from humans and how much of it is from natural sources. Luckily, in a dissertation this year from one of Dr. Davis's doctoral students, Kai Wu, there was a method for calculating this using an analog of Fick's first law of diffusion. So basically, you estimate eddy diffusivity and then use that to get carbon monoxide flux, and then finally use a ratio of anthropogenic CO2 to carbon monoxide that was found by Dr. Turnbull in 2019 using carbon-14 as an identifier. So in order to determine the connection between traffic and emissions, I found the average fossil fuel CO2 flux for each hour of the day during the pre-COVID and post-COVID periods, which I defined using Apple mobility data as a reference. Apple mobility data being data released by Apple on frequency of direction requests from before through after COVID-19. So after removing measurements that were taken while wind was blowing from the west, I compared the average hourly vehicle count on I-74, a highway about 2 kilometers to the north. To see if flux decreased when traffic did due to COVID lockdowns, I compared the average hourly flux for each week and compared them to the average daily vehicle count for every week, again, filtering wind direction. Finally, to figure out magnitude of emissions drops during COVID, I compared the hourly average flux from the two periods to each other and compared pre-COVID and post-COVID average fossil fuel flux as a function of wind direction to get a bit more data on where the CO2 was actually coming from. So the first question, are CO2 emissions patterns similar to traffic patterns? The answer is yes, more or less. Here we have two graphs comparing average hourly emissions from the tower and hourly vehicle counts for a nearby highway for both before and after COVID-19 caused the city to shut down. In both graphs, there are similarities, flux being in blue and traffic being in red, such as the two peaks representing morning and evening rush hour. This suggests that the tower is picking up emissions from the road, but the differences in the pattern suggest that there are other sources present within the tower's footprint as well. So yes, not perfectly, but CO2 emissions do match traffic patterns somewhat. The question is, do traffic and emissions match when viewed across 2020? So comparing weekly average fluxes to daily vehicle counts every week tells a similar story. There is a connection between traffic patterns and flux patterns, but not as much. Both graphs here show that flux and activity begin to sink significantly on the week of March 16th, and we're at their lowest the week of April 6th. However, traffic returned toward normal in a steady but increasing rate, but flux seems to be going upward in a more erratic fashion, mostly because of lack of data. Just wind really just wasn't blowing in the right direction for a couple of these weeks. So there wasn't as much data to work with there. So the final question is, how much did emissions drop during quarantine? So emissions dropped noticeably during Indianapolis's lockdown, according to this graph on the left, especially around morning and evening rush hour. This matches with traffic patterns since most people who stopped traveling during the lockdown went to their jobs at morning and evening rush hours. So that's where the greatest decreases would occur. And if you look at the area under the curve for this graph on the left, you can see that fossil fuel emissions actually dropped by about 58%, as opposed to 43% drop in traffic from the earlier slide. So similar, but definitely emissions are dropping more, suggesting that, again, that there are other sources responsible within the tower's footprint that are also decreasing during COVID, causing the emissions drop to be larger than the traffic drop. The graph on the right shows average anthropogenic CO2 flux as a function of wind direction. So each data point represents like the average flux within this specified bin. So 0 to 20 degrees, 20 to 40 degrees, etc. Emissions are much higher to the east, so i.e. 0 to 180 degrees, which lends strength to the theory that the highway is the most significant source of CO2 in the area. And the fact that decreases in emissions are highest to the east fits with expectations since traffic levels drop significantly, but people are still doing things at home during the shutdown. It should also be noted that tower measurements were used only if wind was blowing from the direction of the highway for this graph on the left. So this lowered the likelihood of the tower picking up other sources, but also meant fewer data points and high uncertainties, which you can see here. And it also did not help that Indianapolis's lockdown only lasted about 4 weeks, further winnowing the number of data points. So that's why there are high uncertainties right here. So how much did emissions drop? Significantly, like I said, about 58%. So especially in the direction of the highway. So basically, overall, the results of this project indicate that the eddy covariance tower is good at detecting traffic emissions. Eddy covariance would be a good choice for monitoring future decreases in CO2 emissions despite the high uncertainties. This tower was actually meant to measure CO2 from the urban forest to the west, so not the road to the east. So, so that's why there wasn't as much data to work with from the highway. So a tower specifically placed to pick up primarily traffic emissions should have lower uncertainties and definitely interesting results. So in future efforts to curb human emissions are made, longer planned ones rather than the unplanned COVID crisis, eddy covariance will definitely be an effective means of quantifying our successes and failures. Any questions?
Thanks, Eli. Questions for Eli?
Hi, Eli. May I ask a question?
Yes.
How does the prevailing wind vary, kind of maybe like in a diurnal cycle?
Yeah, so mostly it comes from the southwest, if memory serves. So it just doesn't blow from the east very often. Like generally, like when I filter it by like just use easterly winds, 0 to 180, 0 being north, 180 being south. I usually have like about 100 data points to work off of like over the entire like 24 hours. So.
Eli, what about truck traffic during the COVID lockdown?
Yeah, so that could be another source of, another reason why drops could be higher, because like trucks versus cars, like they're definitely like they dropped at different rates. Cars dropped by a lot, like more than half, but trucks, they only like dropped by, I don't have the numbers in front of me, but they dropped significantly less. So they could be, that could be throwing things off.
Great. Well, we better move on to our next presentation, which is also about carbon dioxide in the atmosphere. It's by Chris Larson. He's a meteorology major at Texas A&M University, and he's going to be talking about detection of changes in CO2 emissions in State College, Pennsylvania. Chris?
All right, thank you. 1 second. Okay, detection of changes in carbon dioxide emissions in State College, Pennsylvania. And I'm Chris Larson, and I had special help from Natasha Miles and Shaw Finn. And so just a little bit of background, many cities around the world are making pledges to reduce their carbon emissions, and traditional methods to assess carbon emissions are accounting-based, and they can be time-consuming and are prone to systematic errors. And so the atmospheric approach that we're going to take provides an independent assessment. So just a little bit of background about State College. State College is a municipality in Centre County located almost in the center of Pennsylvania. And it's also home to Penn State's main campus and can be described as a college town. And population varies widely as things like collegiate events and academic schedule brings thousands of people to State College or thousands of students return home. And so cavity ring down spectrometers to measure CO2 dry mole fractions were set up across State College from November of 2017 to February of 2018 at 3 sites. And they're at the Rock Springs Research Farm, which is the blue pen, the Walker Building, which is the green pen, and then Hauserville Elementary School, which is the red pen. And during this time period, there were 2 home football games, the first of which was also homecoming, Thanksgiving break, and winter break. And you'll also notice there are 2 power plants on the map, and those are also the only 2 power plants in the county. And it's West Campus Steam Plant, which is the orange pen, and then the East Campus Steam Plant, which is the purple pen. And then University Park Airport is also shown, that's the yellow pen, and that's where I got wind and temperature data. And then there's also windrows pictured on the bottom right of the map, and it's oriented the same as the map with north up. And so that shows the prevailing afternoon wind direction. And so you can obviously see most of the wind is coming from the west and southwest. And the radial axis on that windrows is the probability that wind came from that direction. And so this is the 2016 greenhouse gas inventory for State College. And this is a good example of the traditional method I mentioned in approach to assessing carbon emissions. And it's hard to pinpoint exactly where the emissions are coming from and get an accurate number. And so it's important to point out that they attributed 12% of greenhouse gases in State College to transportation and mobile services. And so we're focusing on traffic mostly and how it affects CO2 concentrations, as vehicle exhaust is a big contributor of carbon dioxide. And so on the left is the hourly CO2 that was measured, and the analysis period was chosen to be November 2nd, 2017 to February 5th, 2018. And so you'll see on the x-axis, DOI is day of year, and that goes from 306 to 401. And then Hauserville was decommissioned on December 5th, 2017, and Rock Springs was decommissioned on February 5th, 2018. And on the right is the afternoon average CO2, and so that's each day. And so I added some event days just to get a better idea of when the events or the breaks are. And the afternoon in our case was defined as 1 to 4 p.m. local standard time, and we're using afternoon concentrations since conditions are well mixed and nighttime conditions are difficult to model. Hauserville was very similar to Rock Springs, as you can see, so we used Rock Springs as the background site, which helps us because it allows the analysis period to be much longer, and we used Walker Building as the downtown site. And so next I calculated CO2 enhancement, and that's calculated by subtracting the afternoon average CO2 dry mole fractions of the background site, which was Rock Springs, from the downtown site, which was the Walker Building. And so enhancements are affected by both atmospheric conditions and the emissions in between the sites. And so I just wanted to point out also, there's only one point in which Rock Springs measured a higher CO2 mole fraction than the Walker Building. And so here's just a quick and easy way to see the average enhancement over each time period. And so you can easily see the first football weekend is the highest. Remember, this was also homecoming. And then the second football weekend was next. And then Thanksgiving break was the least, with winter break following as the second least. And the other is all the other dates in the analysis period range, and it's sort of like a normal enhancement you would see on normal days in State College. So what exactly affects CO2 enhancement? Winds increase the mixing and dilution of CO2 emitted into the atmosphere, and so usually stronger winds mean lower CO2 concentrations. Also, the planetary boundary layer height varies throughout the day, and so it's higher during the afternoon when solar radiation heats the ground, and thus convection occurs, and that causes turbulent mixing. At night, you usually have nocturnal inversions and or a lower planetary boundary layer height. And so emissions during the nighttime get trapped near the ground as the ground cools air right above it, and pollutants can't rise and dilute. And also vehicle exhaust also contributes to CO2 emissions, as I mentioned, and that's important to factor into looking for prior fossil fuel CO2 emissions. And in areas of increased traffic, like urban areas or cities, you usually do see higher average CO2 concentrations. And so I also included a scatter plot of the afternoon average wind speed and CO2 enhancement. And you can see a slight trend as the wind speed increased, CO2 enhancement decreased. And that makes sense because increasing wind speeds would advect the CO2, mix it throughout the atmosphere, and dilute it. And just a note on the prior fossil fuel CO2 emissions, we did look into the steam plants on campus, but the results were deemed inaccurate because the steam plants were to the east of both sites that we used, and the winds were primarily from the west, so it wasn't getting an accurate reading. And we were able to use cell phone usage as a proxy for population and traffic. And so you can see on the left, there's huge influxes of people or large amounts of traffic during football weekends, especially Friday and Saturday, and then lower than normal phone usage or people and traffic during the breaks. And so I created a scatter plot on the right, and that's cell phone usage and CO2 enhancement. And there is a trend visible as there were more people than normal in State College, CO2 enhancement increased. And that makes sense because there's more people on campus going to the game, tailgating, and doing things like that. And so next I use heating degree days as a measure of, just use heating degree days to see how it reacted with CO2 enhancement. And so heating degree days are a measure of how cold the average temperature was on a given day. And so I used all the temperature data from University Park Airport, and I used a base temperature of 65 degrees Fahrenheit. So for example, if you look maybe right here where it says this day had 60 heating degree days, that means the average temperature that day was 5 degrees Fahrenheit. And so that helps energy companies get a sense of how much relatively the demand was on that day, and thus how much energy was produced, which is proportional to the emissions by the plant. And so on the right, I plotted heating degree days versus CO2 enhancement. And you can see as it got colder, CO2 enhancement decreased. So why are we seeing CO2 enhancement decrease when the plants are presumably increasing fuel consumption, emitting more CO2? Again, it's possibly because of the location of the plants relative to the Walker building. It could also be because people are using more energy to heat their homes around State College and the county, so that's increasing emissions around the county. Essentially what I'm trying to say is the difference in CO2 concentrations are less as more background CO2 is pumped into the atmosphere than what's usually emitted on Penn State's campus. You could also make a case that it is the coldest during winter break and there aren't as many people on campus, so PSU is closed and you don't have to heat the buildings as much, so the CO2 enhancement is decreased. And we'll know the answer to the majority of these questions when we're able to run a weather model, and that'll help us pinpoint emission sources, whether the CO2 came from elsewhere or was advected by a weather system, things of that sort. In summary, cities are placing more importance on reducing greenhouse gas emissions. We're taking a new atmospheric approach to measure emissions, combining emissions with modeling, and we're going to compare those results to the inventories, and that'll tell us who's more responsible for what amount of greenhouse gas emissions. CO2 enhancements are affected by wind speed and planetary boundary layer height and other atmospheric conditions. CO2 enhancements increase during periods of increased traffic like football weekends. They decrease during periods of decreased traffic like academic breaks. And so in the future, we're going to run WRF to determine the enhancements we expect based on weather and prior emissions. Thank you.
Thanks, Chris. Any questions for Chris? That's time for 1 or 2 questions.
I have a question. How did you use the phone usage? So how do you get that data from? Like, did you
so we actually, yeah, that was a big deal. That's very unique data. So we got that from a colleague who was able to get it from someone in a cell phone company. So I'm able to use it in this presentation, just something interesting to note. If I publish a paper, if I go to a conference, we do have to get permission to share that information. So it's really unique to have that.
Interesting. Anybody else? Did you look at, were there CO data as well as part of your analysis to differentiate sources?
No, just carbon dioxide.
Okay. Anybody else?
Sure, I'll ask a question. I was curious whether or not this is essentially a monitoring exercise or a way of identifying what the different sources are that would be contributing to the overall increases. If it's a monitoring exercise, would this be used to sort of assess whether or not the city is actually meeting its targets, or are there other reasons to go about doing this that I'm missing?
That makes sense. So I would say what I was doing, it was supposed to be a modeling exercise, but I ended up doing monitoring because we were going to use the model, but they're updating Vulkan is what we're using and they don't have that version ready yet. So we're actually going to do that in the future, maybe in the next few months. So I would say, yeah, to answer your question, both. I am doing a monitoring right now, but when we get that model, we're going to see where they're coming from and be able to pinpoint the sources and all of that.
Cool.
Thanks very much, Chris. Got one more talk before the break. This one's also about carbon, but in sediments, and it's by Tori Froh. She's an environmental chemistry and astrobiology and biogeosciences major at Arizona State University, and she's going to be talking about the impact of diagenesis on the preservation and interpretation of paleoclimatic archives. Tori?
Thanks, Ray. All right, so as Ray mentioned, we were looking at the impacts of diagenesis on interpreting paleoclimatic archives, and I was working with Matt Fantel and his grad student, Ben Barnes. So studying ancient climates is an important tool for being able to predict future climate effects. And one of the main ways scientists do this is looking at the rock records, and in particular marine carbonates. And so they take tracers like carbon-13 and carbon-12, and when compared with standards, you can calculate this value called delta-13, and this can be tracked throughout the rock records and through depth, which can then be translated to time. And so you can see in the plot on the right, when you're tracking the delta-13 throughout time, you get these excursion events, which are essentially either jumps up or dips down in the delta-13 value. And these typically indicate disruptions to the climate and the global carbon cycle, and usually correlated with things like extinction events. And so they're important to study, but diagenesis is something that can alter this record and then essentially confuse the correct interpretations. And so diagenesis is chemical and physical processes that occur to the sediments after deposition that can then alter them. And when the carbonates are altered, then the delta-13 record is altered as well. And in particular, we are looking at authigenic carbonate, which is carbonate that precipitates out of the pore fluid in the sediments after deposition. And this pore fluid, due to different chemistry happening, is going to have different delta-13 levels than the original seawater did. And so it drags essentially the delta-13 C value down and makes these negative excursions. And so we are using reactive transport modeling to simulate a simplified sediment column. And so you can see on the left, just kind of showing the processes happening in the sediment column. At the very top, you've got fluid advection that comes through into the sediments, and then you've got diffusion throughout the sediment column that is moving different species around. And as sediments get buried deeper and deeper, they eventually get lithified into rock. And we're particularly looking at this top portion where recrystallization and precipitation occurs, and that is where the authigenic carbonate precipitates. And so it pulls this delta-13 value down because the source of carbon from these authigenic carbonates is coming from marine organisms, which have a lower delta-13 C value than original marine carbonates may, which you can see are a bit higher. And the chemistry involved in what we were doing. So at the very top of the sediment column, you've got aerobic respiration, which uses up the oxygen. And when that's gone, then microbial activity increases and you get sulfate reduction happening. And what sulfate reduction does is it takes this organic carbon and this transforms it into bicarbonate, which is inorganic, and that is basically the source for the authigenic carbonate that precipitates out. And so when you have a lot of this sulfate reduction happening, that's when you get this carbonate authigenosis, which can pull down the delta-13 C record present. And so all of this is being run in a program called CrunchTope. And so there's a lot of complex math behind it that's being calculated through different time steps in our simulations, as well as depth domains. And it includes stuff like conservation of mass and mass transport, total concentration of the different species and the chemistry happening, as well as advective transport and diffusive transport, and simulating all of this throughout millions of years. And so what we are finding is that sulfate reduction, and therefore the carbonate authigenosis, is generating these variations in the outputs that are not related to the exogenic carbon cycle, but look like what those signals were from climate events. And so you can see these are direct outputs from our model, and they show vertically through like the depth domain. So at the very top is the top of the sediment column, and the bottoms would be the bottom of the sediment column. And in that top area where authigenic carbonate is precipitating, we get these negative spikes towards lower delta 13 values. We did run lots of different scenarios in our models, but particularly looking at what impact lithology has. And so lithology essentially is discussing what is the composition of the sediments in the sediment column before this diagenesis was run. And so at first, you see in this one, we have like a thin layer of clay at the top, which is carbonate depleted, and then followed by a layer of moderate amounts of calcium carbonate, the carbonates, and then underneath we have more rich carbonate. And you can see in the plots, so we took the depth domain and translated it to time because deeper depths indicate older rocks. And so you can see in the top portion where the precipitation, the authigenic carbonate precipitation is happening, there's a slight drop in the delta 13. And so this is because with a decent amount of carbonate already present, the new authigenic carbonate doesn't have as much of an impact, but it is pulling down the record a little bit. And when we move that layer down 20 meters, so now that the clay layer is in that sulfate reduction zone, we see that there is a spike downwards in the delta 13 because that new authigenic carbonate can have a greater impact on the bulk carbonate signal. And when that's moved down another 70 meters, so that primarily it is all clay that was in that authigenic carbonate zone, we see an equally deep but now broader signal in the delta 13 because all of that new authigenic carbonate is essentially overriding what that previous carbonate value would have been. And so we can take this and compare it to real life data. And so in particular, I plotted here some data from a couple different papers looking at sediments from the end Guadalupean extinction event. And you can see that equally there is a similar shaped signal in terms of depth and width than what we were creating in our models. And this event too had lithology change. So we had carbonates were earlier in the column, and then in this area where the signal is, it changed to a mudstone, which has less carbonate, and then went back to a limestone carbonate rich lithology. And so this same sort of scenario with lithology changes in real life data at a real life climate event was creating similar signals. And so what this tells us is that diagenetic processes can create signals that are similar to primary signals that were generated by climate events. And so in the future, there are other factors that we can test as well. So besides changing lithology, we can change things like sedimentation rate, ocean chemistry, or porosity to look at, I guess, the range of different diagenetic signals that could be created. And this kind of leads into the question, how can we figure out if diagenesis or climate was the cause of these records? And that will have to be studied more. But overall, I think this kind of goes to show that when we're studying these rock records to kind of piece together and look at different climate events, you have to consider diagenesis in order to most accurately interpret what we're seeing. And here are my sources. Thank you.
Thanks, Tori. Any questions for Tori?
So, Tori, how would this be related to the late Proterozoic? Because there's big changes there. Would there be some connection here?
Yeah, I mean, so this is just kind of showing that like signals cannot necessarily, you can't just assume that diagenesis is not involved at all. Like a lot of different papers looking at climate events are just assuming that diagenesis isn't a factor and that the records they're looking at were just the original records that were there. And so this is just kind of something that needs to be considered, that you can't just assume when like looking at this previous data that it directly came from the climate event and there was nothing else going on. And so some of these signals could be impacted. And even if it's not, like some of it is climate related, some of the signals, the delta 13 like events might be amplified or altered a bit from what they originally were because of the the chemistry and the processes that were happening after deposition. And so a lot of different events could theoretically just be considered. You have to include looking at diagenesis as part of the process in order to like most accurately figure out what caused the different signals.
Anyone else?
I'll take a shot.
Yes, thank you.
I'm curious whether or not there are, very specific events in the paleoclimate record where you expect to see a very large adjustment by having to consider this particular effect. Was there a discussion of that in terms of what eras or what types of events we would expect to see this have the most impact?
Yeah, so we didn't get into that a ton yet. I think that would be a really good like next step direction, but typically, so events that cause these like negative excursions rather than positive are definitely what would be more diagenetic related. And so any, I guess, of the situations where where they previously were just attributed to like more organic carbon burial, and that was just kind of the sum up of what was happening, could be reanalyzed, just taking into account that diagenesis might have had an impact in it. But I think that would be a really good future direction to consider, is pinpointing like exact events that this could be related to.
Thank you.
Great. Thanks very much, Tori. All right, we're only just a couple minutes behind. We're going to take just a little bit more than a 15-minute break, and we're going to start up again at 2:35 with another set of 7 talks. So we'll get a little fresh air or whatever it takes to get refreshed, and we'll see you soon.
The second session is Amanda Garcia. She's a conservation and resource studies major with a concentration in climate and resource management at the University of California, Berkeley. And Amanda, it's all yours.
Okay, gonna share my screen. Oops. Okay. So my project is the historical ecology of global fisheries. I've been working with Christina Douglas and the OBT lab, especially Dylan Davis, who helped me create the database itself. So we're looking at the Western Indian Ocean, specifically the Eastern African countries regarding it. So a lot of the research I found was near Kenya, Tanzania, Mozambique, Madagascar, a lot of the smaller islands surrounding. So what is a database? It's basically just a formal place where data and other information is compiled. What's the significance of creating one, and why will a database for this region of the world be impactful? These are the primary questions that I hope to answer in my presentation. So this is essentially the way that it's being organized. I have a few different screenshot clips that I've taken. So in the top, you can see author, location, time period, scale, all of these different things that we'll be organizing them by. And then more specifically, I've highlighted paleoclimate proxy type, which there's a bunch of different types. You can have coral biomarkers, spatial resolution, which would be either degrees or kilometers, etc., and temporal resolution, which shows up in either centennial, decadal, millennial, monthly, or seasonal if it's extremely specific. So starting with a question, The primary question is really what questions need to be asked. So building a database is a way to reveal what we already know, and it enables us to ask new questions. Compiling scientific literature with a high degree of specificity helps us to avoid redundancy in the field. Fieldwork and archival research are equally essential, and in a perfect world, would sync continuously. So what I mean by that is, as we do more research in the field, we also need to analyze that in the context of its relation to everything else. And so that way we always know what we know and what we don't know. So this is my way of detailing my searches, essentially. This is a big part of the overall work that I've been doing. So I have tried to be as systematic as possible and repeating the same searches. So I'll start with a database and then a search term and narrow it, and then put in different alternatives and so on. So this project is I think one of the most important things about it is that it's a matter of equity. The Indian Ocean is warming at a faster rate than other oceans, contributing to drastic changes in the productivity of coastal fisheries, which has a domino effect of consequences for locals. Access to information and technology is not distributed equitably. And when you think of funding, a lot of the questions that I have are, who gets funding? Where is funding more prevalent? What type of research is being funded over others? When is that research taking place, and why and how? So that's in terms of significance, and then how it's being done. Regional research in the West Indian Ocean is very variable, spatially and temporally. The resolutions can be quite different based on when the research was published. And there's a lot of limitations for not only modern researchers and fisheries managers and scientists, but for people that are doing archival research, such as me. There's limitations in terms of paywalls and other things like that, which I've noticed even in databases that I specifically have access to. I'll still run into issues where I can't get a PDF or a data collection unless I request it from a library, and then that takes more time. So there's other constraints involved. So this is an image of fishermen in Kenya with the credit to Katie MacLeod. So it's basically just fisheries are foundational for a lot of people in terms of food and income. It's a matter of resource security and food security, and really livelihoods are at stake. I think I messed up the slide order slightly. So key takeaways are that fisheries management research along the central eastern coast of continental Africa is lacking. Present research concerned with deep timescales has a difficult time calling upon archaeological records, and modern researchers are increasingly approaching climate and resource issues in a more layered and dynamic way than before. So what I mean by that is taking into terms socioeconomic status and a lot of other things that impact the way that people live their lives, and looking at ecology with a human lens as well, and regarding humans as heavily tied to their environment. So this is one of my Excel spreadsheets. what you can see, like there's definitely still some holes. So that happens when I can't necessarily see the entire publication, and a lot of the time abstracts don't have the detailed information that I need to organize it. So this is going to be an ongoing process of requesting things. And yeah, I'd say overall, I'm really happy to be able to continue working with the OTB lab, and I hope that this evolves into a bigger project and expands into more locations that are also facing crucial climate issues. And yeah.
All right, thank you, Amanda. We have time for a few questions.
Hey, I liked your presentation a lot. Is this, one question is this historical going back to when? If these are archaeological, I mean, I know those don't come with timestamps, but about when is this period you're looking at?
All right, so I'm mostly collecting, I guess that's one of the questions is how far can we get? I think in this specific region, there's a limited amount of evidence. So I've seen things that go back as far as a few thousand years in terms of just coral records, but there's climate reconstructions that can be millions of years. So it's extremely variable.
Okay, my quick one, Amanda, before Rebecca comes up, is how do we open up the access? You know, you're saying it's not free, it's all these issues. What are some of your ideas about improving access?
That's a really good question. Obviously, if you are a part of a university system, you have certain access that you get, which technically also isn't free because I pay for it. Like, and I think it would probably be a systemic issue of the way that we manage our informational resources as well. But I guess with this database, I'm trying my best to take the time to request everything so that I can have everything in full text, like all of the journal articles and data books. That way it can be published without any extra steps for people to have to follow up with a link or something like that. So I guess that's my main focus, is making sure that everything I put in the database is completely open access.
Who's there?
Thank you.
Hi.
So please mute your mics if you are going to answer the door. Now, our next speaker is Rebecca Beal. She is a major at the Florida State University, home of Krishnamurti and the great hurricane forecasting there. So take it away.
Okay, let me get my screen set up. Okay. Hi, everybody. My name is Rebecca Beal, and I'm here to present my research on growing food in a changing climate. My mentors have been Dr. Jenny Evans, Dr. Jose Fuentes, and our grad student, Drew Pulaski. So we're all here at this REU, and of course, we've been learning about the different impacts that climate change is representing on pretty much all aspects of our lives. And one of the most vulnerable areas is in agriculture. Agriculture is vulnerable both to changes in weather and in climate. So we feel that in order to study what the effects of a changing climate might have on agriculture, we really need to establish what the pattern is between weather and agriculture today. And kind of one of the jumping off points for this research comes from Drew Pulaski's, this is one of his figures from his talk at the AMS conference. This is a future projection with different models in the near future for 2021 to 2050, and in the far future from 2071 to 2100, using different emission assumptions. So low emission, medium emission, and high emission assumptions. And really the conclusion of this is that on the daily average, we might be seeing an increase in precipitation to the north and a decrease to the south. For the purpose of this study, we've been looking at northern Iowa. So in our region, we might be seeing an increase in rainfall and wetter years on the average. What we'd like to know is what might this indicate for crop production? And we're studying this kind of looking at, will wetter years produce better crops? So in order to do this, we start by creating a simulation, and we use APSIM, which is the Agricultural Production System Simulator. It's a very customizable and powerful model. It takes different modules. So some of the examples here are weather, soil, water, and management techniques. And then these are some of the variables that you can change within it. So really you can customize it for physical location as well as for the different management practices taking place in your run. And we wanted to, our goals here were to create an APSIM environment that represented a physical location and that would recreate real results. So we turned to the literature and we found one that is really applicable. Their research project took place in two distinct steps. And more detail are in the bullet points, but basically their first step was to run almost 100 unique empirical experiments across Iowa and study different location, and within those different empirical studies, they changed the crop cultivars, they changed the location, they changed the management techniques, and then they took measurements at many different growth parameters, took those measurements and stored them away. The second step was recreating the experiments in APSIM. So again, they made almost 100 different APSIM environments to recreate the experiment that they'd set up. They ended up finding across, I think they used 19 different variables in the APSIM environment as their output. And for all the different runs and for all the different variables, they got a root mean squared error, a typical root mean squared error of 25%. And when you look only at the corn, biomass, and yield, they were typically looking at differences of about 17% and about 23% respectively. So taking what they've done and worked on and putting it into our research project, we really recreated one result. So we wanted to use a monoculture of corn with no intercropping techniques. So there was no sharing the field with soybeans. So we used a monoculture of corn with no nitrogen management practices. And the location that did that was in Sutherland, Iowa, which is in the Northwest. So we used the physical variables for Sutherland, Iowa, and we used the management practices from that experiment. We were with a little bit more modification, we were able to create an environment that output an average annual yield and biomass differing only by about 7% and 25% respectively. And so once we had an environment that we were comfortable using, we used it to create we used it to try and make a historical model of what had happened in the period 1979 to 2013. So we used historical weather data and the APSIM environment that we'd set up. And this is what we're seeing. So the orange here is the yield and the blue is the biomass. And some things you can already see, the biomass has a much greater variability than the yield does. And between that and the yield not being reproduced as well in the model, we used biomass as our stand-in for crop production variable. Because we want to go back and say, okay, how does the weather surrounding that year compare to the yield, the biomass that we see during that year? So this is how we classified our data. We ended up saying, okay, the top third producing years are high biomass years, and the bottom third producing years are low biomass years, and in the middle are medium. So this is what that distribution looks like over time here. And this is how we started to compute our results. So going back to our question being, will a wetter future kind of cause a more productive crop? we started with, well, what have we seen historically? Do wetter years produce better crops? And it's important to note this is wetter in terms of the total. So does a total of cumulative rainfall, more rainfall during that annual period, mean better crops? And we can see here sorted by high, medium, and low years. So really just looking at if there's any pattern that's stronger in some years than other, in some categories than other, we looked at the correlation. And what we really see is that there's no correlation across any of the years, especially not in the high or in the low, between total amount of rainfall and total biomass produced during that year. In the medium, we are seeing some kind of correlation, but we usually say that significant results start at about 0.5, and so this is still less than that. So we wouldn't really call that even significant. So this wasn't, so basically the conclusion we reached is that high harvest years are not correlated to the total cumulative amount of water during that year. But we still do feel in our next step of research that a better correlation would be when the rain falls, so that if we could track the variability if it falls during the harvesting period or before that or after that, that's what would correlate stronger to the actual biomass. Okay, so thanks everybody. This has been a really great opportunity and I was so glad to participate. Does anybody have any questions?
Can I ask a question? So Rebecca, very interesting. Would you mind elaborating a little bit more about the difference between biomass and yield, especially why yield does not change much when biomass actually varies quite a lot?
Right, so biomass and yield in this term, this is all about corn. And so the biomass is it's the stalk, it's the leaves, it's the actual plant itself. And the yield is only based on what they harvest. So it's the ears of corn itself. So that also explains the just difference in magnitude that we're seeing. And of course, you're going to get very little, a couple ears of corn off of one huge plant. As far as why we're seeing that variability, or really that lack of variability in yield, there is some, and it does correlate just as high biomass years produce high yield years. There's that one-to-one relationship, but as far as why it's not quite as strong, I am not sure about that.
Okay.
Sorry for giving a half answer.
Another quick question.
I have one, Rebecca. It's really interesting. I might missed some part of your talk. Is the different places they have all relatively similar total precipitation? I guess I wonder if there's some kind of let's see, annual. Okay, so they do have quite some different. I wonder if that if you normalize the total amount of precipitation, if it's it would make a difference. Like the relative amount of flooding compared to the overall.
Right. That would be an interesting step to take, I think.
Okay, well, more work to be done. So I think we'll go to the next presentation, which is, everybody's my favorite person in the REU, but Paige is one of my favorite people. So she's from Central Michigan University, and she is a meteorology major and actuarial science major, and she's up next.
All right. All righty. Okay, thank you, Greg, for the introduction. I really appreciate that. So as he said, I will be talking today about the climate change impacts on apple bloom dates. My name is Paige Elliot, and I worked on this project with Dr. Chris Forrest. Dr. Jose Fuentes, Dr. Rich Marini, Dr. Ray Najar, and Drew Pulaski. So our northeastern fruit-bearing trees are blooming earlier. If we take a look at this map here, adapted from an Earth Science journal, you can see that there is a negative trend in the Northeast in days per decade for our first bloom dates. More specifically, that red and orange color indicates that there's a -2, maybe even -3 day per decade trend for our first bloom dates. Now, why do early bloom dates matter? Early bloom dates matter for a multitude of reasons, but with the main reason being that with an earlier bloom, we run the risk for later season frost. And with a later season frost, it can end up killing the flower itself. And once the flower dies, it is unable to produce any fruit. So for the purposes of this research, we wanted to pinpoint the exact aspect of climate change that was affecting these early bloom dates in order for us to further prepare our farmers and agriculturalists for the incoming impacts of climate change. So if we take another look at this image here on the right, those black dots indicate the 4 locations that I looked at in the Northeast for my research. So the 4 locations being Rock Springs, Pennsylvania, Winchester, Virginia, Biglerville, Pennsylvania, and Hudson Valley, New York. Now this image here is a graph of bloom date per year for all 4 of our locations. Now bloom date is determined a couple different ways, but the most common way that bloom date is determined is when farmers see that all of their flowers had opened, but right before the petals have fallen. So going back to this image here, you can see that there is a lot of correlation and some similar patterns between the bloom dates and how they function. So I want to pinpoint a couple specific instances here. So in 2011, you can see that there is a spike or a later bloom date for all 4 of these locations. And then in 2012 here, we have a pretty dramatic trough or a pretty dramatically early bloom date for all 4 of these locations. Now, seeing these patterns, we know that this isn't something that one location is doing independently different than another location. We know that this is phenological. We know that this is something that is impacting all 4 locations, which would be its climate. So for here, I took some temperature data. Some of it was imported from GHCN station data, and some other being from GridMet products. And so I plotted on the left here, average March temperatures for all 4 locations per year. And then on the right here, we have average April temperatures for all 4 of our locations. And it doesn't really come as much of a surprise that they correlate really nicely with each other. And that's due to the fact that they all experience a very similar climate and they're all in the same region. But I did see some noticeable impacts that reflected what we saw in the bloom date graph earlier. And so I'll point you to those as well. So if we look at 2011 here, we have that peak, or excuse me, we have that trough or decreased average temperatures for March. And then in 2012, we have that peak or increased average temperatures for March, which seems to sort of mirror what we had for our bloom date. So I wanted to plot those 2 against each other and do some statistical analysis to see the impact that temperatures had directly on our bloom date. So here I have some linear regression graphs. On the left, we're looking at bloom date for average versus average March temperatures. And then on the right here, we have bloom date versus average April temperatures. Now, like I said, this is linear regression, and this is representative of only one of our locations, which is Rock Springs, but it represented all 4 locations very nicely, so that's why I chose this location. But for our March temperatures, we saw a correlation of -0.67, and for April, we only had a correlation of about 0.50 for bloom date versus temperatures. And that was pretty representative all across the board, that March temperatures independently had the greatest impact on bloom date than any other month independently. And so if we look on the March and April temperatures, another thing that's slightly concerning is that we had some pretty dramatic outliers. So one way that I tried to take into account those outliers was plotting the average March temperatures and April temperatures together against bloom date and seeing my results. And I got some really nice results when I compared those 2 together against bloom date. So I got a correlation value of -0.830 when I combined average March and April temperatures together and plotted them against bloom date. Now that negative correlation just means as our average March and April temperatures are increasing, the days since January 1st are decreasing, or we're seeing an earlier bloom date. Now, I went through and tried a couple different combinations with this. I looked at, February and March. I looked at February, March, and April, and all of them did correlate, but none of them as dramatically as March and April together. And that's just due to the fact that those January and February months didn't have as big of an impact in correlation with the bloom date as a whole. So the last thing I'd like to talk about is growing degree days, and I'd like to make some speculations based on my research about growing degree days. So it was under my impression that after chilling had been satisfied, 100 growing degree days would be enough to break the apple tree's dormancy and allow the tree to bloom. So for the purposes of my research, I calculated growing degree days through that equation down below, where I took the maximum temperature and added that to the minimum temperature and divided by 2 to get a daily average temperature, and subtracted a threshold value. Now for apple trees, that threshold value is 7.22 degrees Celsius. And what I did with that is I kind of plotted against the average March temperature. So I took, on this graph above here, I took the growing degree days for March and I plotted it against average March temperatures and did a linear regression analysis for that. And I got a correlation value of 0.87. That wasn't super surprising because growing degree days are direct, a direct product of temperature. But it does allow me to make some pretty cool speculations based on being able to predict bloom dates using this growing degree day idea. So I can speculate that a growing degree day in March matters more or has a greater value than a growing degree day in February. And that's just due to the fact that those average March temperatures independently had a greater impact on bloom date. But like I said, with time constraints and stuff like that, I was unable to do this research on my own, but it is definitely an area that yields more research and could allow a greater prediction of how to predict our bloom dates. So I just wanted to thank the National Science Foundation and the Penn State staff for giving me this opportunity to do the research on our beloved fruits. So I can take any questions now.
All right, questions?
Hi, Paige. This is Christina. Do you know if farmers are more concerned about frost or really hot days?
There is concerns with both of those, but frost is sort of the main concern. Once temperatures exceed about 90 degrees Fahrenheit, you can lose a crop. And there are other aspects of climate change like hail and storms that can actually knock the apples off the tree. But the primary concern here, like this year, for example, I believe we've lost 80 to 90% of our crops due to that late season frost that we had in May. So that's definitely our main concern once it comes to looking at bloom dates and climate and how that affects the yields. Thank you.
Paige, this is Dr. Evans.
Hi.
So, hi. Can you, let me do this. Oops, I'm not there. Can you use your analysis to help us think about, to help predict a crop yield?
Definitely. Definitely. So the problem with my research is I started off kind of focusing really hard on those growing degree days, and that kind of led me to a lot of dead ends. And it wasn't until later on in my analysis where I started to, figure out that those monthly average temperatures had the greatest impact on our bloom dates. But definitely, for sure, if we take a look at this graph, I mean, the correlation is pretty striking. So, and there aren't any, super extreme outliers, anything, nothing more than about 5 days. So this can definitely be used to predict apple bloom dates for the future. And that is somewhere that I'd like to move further with the research, because I think it could give us a good gauge of where we're going and what could happen in the future. Thank you.
Thank you.
All right, well, we're going to move on. And Paige, thanks for leading the discussion a few weeks ago about the Flint water crisis. That was very important from my perspective and very nice of you. Okay,
Thank you.
We have another of my favorites. So people are like, Professor Fuente said, how can you have favorites? I said, they're all my favorites. I'm just yelling them out, just saying, hey, they're my favorites. The next favorite from Colorado, of course, is Elana Cope, and she's a chemistry major at CSU. And you're up next.
Thank you so much for that introduction. Let me share my screen. Okay, can you all see? Okay.
Yes.
So I'm going to tell you a bit about data visualization software for tracking the foraging patterns of bees with radar. So I've had the pleasure of working with 5 wonderful mentors, Dr. Fuentes, Zach Moon, Dr. Urbina, Diego Peñalosa-Pante, and Dr. Lopez Uribe. And my project is about bees. So pollinators are declining due to global climate change. And this is really worrisome because pollinators, insects specifically, account for 75% of the world food budget. So if we lose pollinators, we lose food. And the decline of pollinators can be broken down into biotic factors and abiotic factors. So biotic are living, the parasites, the predators, diseases. Abiotic are air pollution, rising temperatures, drought, that kind of thing. And of course they play into one another. But we are interested in the abiotic factors. Specifically, we're interested in air pollution. So air pollution affects bees' foraging patterns by degrading floral scent plumes. So flowers release these organic molecules into the air, such as linalool, that's one of them. And bees have these neuroreceptors in their antenna, and they pick up these floral scent plumes and can find the flowers. However, in a polluted setting, then the pollution molecules, such as ozone or NOx or the hydroxyl radical, will react with these floral scent molecules and create different molecules such as acetone, formaldehyde, these other organic molecules. And then the bees' neuroreceptors can't pick up those molecules. So the bees get confused, their foraging time increases, and they have a harder time finding the flowers. So we want to learn more about this. So the team I've been working with at Penn State has developed a radar system to track the foraging patterns of bees. The way this works is the radar will have a transmitter, transmitting antenna, and that will send a pulse. And there will be a tiny instrument attached to the bee called a transponder that has a diode, and it sends back a pulse at double the frequency to the antenna. So then you can measure the time in between the pulses and put that into the physics formula, velocity equals distance over time. We know the velocity, that's the speed of light, and we know the time, so then we can track how far the bee is from the radar location. So the system that has been built by my team looks like this. You have a transmitting antenna, and that communicates with a transponder right there. And then since we're during a pandemic, the engineers on the team have also developed a simulator, and then that sends the same data to the receiving system that this would have in the field. And this is our receiving system. We have a Raspberry Pi computer that takes the frequency and turns that into more logical units such as meters and latitude and longitude, and then sends it to a master computer. And the master computer is the focus of this project. What happens to the data when it gets to the master computer? And so I've been helping to build a software system that will work up that data when it gets to the master computer. So we have a master script that will communicate with the radar system. You can tell it, how many recordings you want and how long each recording will be. And then it receives data from the radar system, reads that data and appends it to a master file, and then visualizes that data in the form of graphs and histograms, things like that. Since, again, we're building this during the pandemic, we've also designed a file generator. That way we'll have some sample files and we can make sure that the rest of our system is working, you know, just in place of this part of the system. So this is what our visualization is going to look like. We have the harmonic radar settings on the left-hand side of this graphical user interface. And then we're going to have the data visualization on the right-hand side. We'll have various graph options. You can choose polar, Cartesian. This georeferencing graph is going to show the bee's location on a map. And yeah, so you can choose these, and the way we figured out, or the way we coded these graphs was by using sample data. So since we're not in the field, we have taken some data from already published data sets. This is from Dagan and colleagues. There's a very interesting paper about how bees perform orientation flights. And we basically used the scaling of this figure and took the coordinates of this flight trajectory, turned them into the file type that we used, and then used those files to build our software. That way we can see that the graphs look okay, and we can make sample data sets and, you know, create new files, that kind of thing. Another thing that this program does is it displays data like calculations. So you can see step distances and step angles. So every few seconds, the radar sends a point and you can see the distance in between points. We calculated that using the distance formula, and the step angles, which is the angle in between those points. You can get that from the arctangent of the distance in Y over the distance in X. And then at each of these step angles, you can see how far the bee traveled. And, you know, so like I said, a lot of this work has been through modeling, but it's all for the purpose of being ready to employ this software and this instrumentation in the field. And we're very excited to see what comes of this. Excited to see how abiotic factors affect bees. And, you know, just some take-home messages. I've had a really wonderful experience learning about bees in their natural habitat. They're really smart. They have spatial memories and they can adapt to different landscapes, and they perform exploratory flights in a new area. And it's also really important to learn about the different factors such as air pollution that are affecting the bees. So that's why this radar system has been built, and that's why I've been helping to make this software so that we can help observe and quantify information about these flight patterns. So I'd like to offer a really warm thank you to my mentors. They have been so much help this summer, and to the program directors, Dr. Najjar and Dr. Jenkins, and all of the faculty that have helped put on this REU, fellow REU students, the NSF for funding. This has really been a wonderful experience, and I'm so glad I was able to take part in it. I'd be happy to answer any questions.
Questions?
Yeah, I had a quick question. How does the transponder impact the bee?
You know, that's a really excellent question. In all of the papers that I read, it basically said, like, we tested the bee's flight with and without the transponder, and it didn't really impact the bee's flight. And the transponder, I think, is about 1/5 of the bee's weight. And so it looks big relative to the bee, but I don't think they have too hard of a time flying with it. Basically, all the papers said that it didn't really impact it. So, yeah.
Another question.
Is there is the weight of the transponder about the same weight as the pollen it would carry back or the nectar it would carry back on the way back to the hive?
Oh, I don't know. I'd have to get back to you on that. I would imagine it would be heavier, but yeah, I can get back to you on that.
I've seen some pretty loaded down bees with pockets and pockets of pollen, so I figured they might be heavy.
Yeah, I'll get back to you on that.
Thanks.
If you send your email, I can send it.
Sure.
All right, Elena, that was really good presentation, and thank you very much. Next, from the University of Vermont, majoring in civil engineering, and somebody who I've been feeling very grateful to know for the last 8 weeks. We have Dia Brown, and I might say before Dia goes up that she has been really at the forefront of working with her administration to address some of the issues of inequity. And so I don't know how much sleep she got this summer, but I know she had a gazillion meetings, and I'm really proud of her. So Dia, you're up next.
Yeah, howdy y'all. So my presentation is on particulate matter levels, rainfall, and temperature as it relates to COVID-19 cases and mortalities in Ghana and South Africa. And so moving into a bit of an introduction to the project. So worldwide coronavirus cases have now gone over 16 million, and with around 700,000 deaths. And that number is continuing to go up by a lot. And so it's already been shown that greater PM 2.5 pollution, which is the particulate matter of 2.5 micrometers, has an association to increased COVID-19 mortalities, at least in the US. And so disparities do not exist in a vacuum. And so it's likely to occur in other areas such as Ghana and South Africa, which there's where Ghana is. And then South Africa is right over there. And so a bit more of an introduction. Sources of PM 2.5 can be from a variety of things, such as natural resources like Saharan dust, which we saw in Texas earlier this summer. It can also come from human-made pollution, such as slash and burn agricultural techniques, or poor air quality regulations for industries and even older cars. And so all of this on top of colder temperatures in South Africa, which South Africa experiences seasonal weather like summer and winter, and right now, like they are in their winter season. And Ghana, which has wet and dry seasons, which the wet season occurs from March or April-ish to October/November. These can contribute to increased mortality in COVID-19 cases. And so going into my hypotheses, the first one is that in the similar way of the case study that was done in the US, the higher PM 2.5 levels will cause increased COVID-19 cases and mortalities within Ghana and South Africa. So when restrictions were tighter, people were not able to go out and industries had to halt. And so there have been previous links to health conditions such as like respiratory and heart diseases with PM 2.5. And so the other hypothesis is that increased precipitation will also increase COVID-19 cases and mortalities within Ghana, because when there's more rain, there are more communicable diseases like influenza and pneumonia spreading, and people are staying indoors, and so there's more likely risk for transmission. And since air is not being filtered, that also increases that transmission risk. And so, like I said, though Ghana doesn't have significant seasonal changes, it goes through the wet and dry season, and it does get a little bit colder then too. And then the third hypothesis is that with colder temperatures, there'd be increased COVID-19 cases and mortalities in South Africa, with that same idea of the communicable disease spread, as well as just people being indoors more. And so the methodology that I use is, so these are where all my data came from. So for the air pollution, the particulate matter and temperature data that comes from Purple Air website, which there are these little sensors that are all over the world, and that data is public for anyone to look at. And then the COVID-19 cases and deaths came from the WHO's coronavirus dashboard. There's a bunch of different dashboards, but that one has every single country available on there for every single day that it's reported. And for precipitation, I use NASA's Giovanni database. And so I looked at 4 cities within the 2 countries. So I looked at Accra and Kumasi, and Cape Town and Pretoria. And so something that's important is within the regions of Ghana, the Greater Accra region and the Ashanti region, which these cities are in, have the top 2 highest case numbers in that whole country. And then it's the same thing for Cape Town and Pretoria in terms of what provinces they're in. And so, as I said, like with the WHO COVID data, it's daily data from every country. So there's a lot there. So I had to re-index using pandas and Python so that it was only showing me Ghana and South Africa. And so I also had to resample the data for COVID-19 to be weekly, just because sometimes, like Ghana in particular, there wasn't always a daily number. So it would kind of dip randomly, and it wasn't necessarily that no one was getting it or passing away. It was definitely a lot more to do with just not reporting. So having a weekly data set made it more accurate of a picture. And so looking at these are the charts for cases within and mortalities within these countries. And so an important note is that this is from March through July. And so there are over 400,000 cases in South Africa and around 6,000 deaths. And within Ghana, there's 30,000 cases and around 161 deaths. And so another thing that's really important to point out is even though the death number seems low in Ghana, 56% of their population in Accra is below the age of 24. So it's a generally very young population there in other parts of Ghana. And there's also a really intense stigma around reporting loved ones dying from COVID-19. So there are chances that the numbers are larger than what's being said. And it's also really important to remember that these are not just numbers, that these are people who are passing away every single day in this pandemic. And another thing to keep in mind is WHO air quality standards and EPA air quality standards. These numbers are super important to look at as you're looking at these cities, because all of them surpass this most of the time for what is considered healthy. And so within South Africa, as restrictions relaxed from a level 5 to a level 3 on June 1st, numbers skyrocketed a lot. And so a level 3 allowed for businesses to reopen, and many of them went back to normal. People were able to go outside and be in close proximity with little room for social distancing. And so right there is around June 1st. And then that's where the WHO standards are, and that's where the EPA standards are. And so those blue dots are where the PM 2.5 levels are for air quality, and all of them are going far above. And you can kind of see the same thing happening here in Pretoria, in Cape Town. And so looking at the same kind of thing in Ghana, you notice that the EPA standard doesn't even make the chart for this one. So none of them are actually up to EPA air quality standards. And there wasn't really a whole lot of restrictions to begin with. There were no level 3s in Ghana. It was kind of more that there was a ban on social gatherings in Accra and Kumasi because those cities were experiencing so many cases. But then those had been relaxed and have been continually still pretty relaxed. And so as you can see here, that's where the WHO air quality standard is again. And it's still kind of the same thing. And as you can see, within all 4 cities, there's a trend going upwards between those air quality measurements and the mortalities. And so looking at temperature within South Africa, within Cape Town and Pretoria, as you can see, they were going through winter. So now the temperatures have been dramatically going down, and those cases are still going up. And another thing that's important to note here is that influenza season starts around April in South Africa. And so there's the transmission of multiple diseases at the same time. And so wet season also plays an active role within cities in Ghana. As said, it's March through April to October/November. And as you can kind of see here, where the peaks are is also around where cases of death start going up. And so another thing that's important to note is there's kind of a vacuum right here. It's just because the data that I had went up to July 12th for the precipitation. And so that just needs to be filled in with the latest data. And so some conclusions from this is that the PM 2.5 hypothesis for all but Kumasi seem correct. Kumasi is the only one where it's kind of a negative correlation, but at the same time, those air quality values were still significantly higher than they should be. And the colder temperatures are also shown to be a concern. And so it's kind of, it looks kind of more difficult to read for precipitation, but you can kind of see that it's also been wetter than on average in the past for a wet season in Ghana. And so what this means for the future is, in terms of policy, I looked a lot at how the policies were impacting this as well throughout, but there's definitely not enough time to really talk about all of them. But South Africa recently changed what a level 3 is to make it stricter, and also put out procedures for mass burials. And so the economic and human impacts are huge. And so for some next steps, I definitely want to do some lag correlations and look and see if there's any more stark correlations between those two. But in this preliminary finding, it's already very stark. So yeah, that is all. There's my sources. I definitely feel like I went over, but that's okay. So thanks, y'all. I really appreciate it.
All right, we got time for a question.
I'll ask a question. So I'm curious whether or not the African countries are less connected through air travel, and so the transmission within the country is really coming from the internal dynamics of the country versus a super spreader coming in from another location and then starting off multiple cases. Do you see any of that? Because the curves really looked like they were going up pretty steadily without jumps.
Yeah, so it's definitely, there's a lot of restrictions on who was able to come into those countries in the beginning. Less so now, but I still don't think there's a lot of travel, at least through air coming in. Beyond cars, there's not a lot. It's mainly just because the makeup of all of these cities is a lot of close proximity housing. And so if one person gets it, you can give it to your neighbors very easily. And there's a lot of open markets. And so like a lot of it is just community spread at this point, less so from outside people coming in.
Cool, thank you.
All right. Well, let's go to the next talk. And that's Yanqiu Guo of Queensborough Community College in New York City. She has following a bachelor's in mathematics. You're up next.
Yeah, thank you for your introduction. I'm appreciate it. Okay, so good afternoon, everyone. My name is Yanqiu Guo from New York City, Queensborough Community College. Today, I'm gonna talk about my research project that I'm doing with Dr. Penn and Dr. Li. And this project is funded by NSF Research Experiences for Undergraduate Program. And our project focuses on determining non-stationary dynamic transition during an RC interaction field campaign. So why should we choose this field to study? That's because the demand for energy keeps increasing. And as we all know, when we burn fossil fuels to get energy, a lot of carbon dioxide and sulfur dioxide are produced, causing serious air pollution. So we thought of developing some new energy like wind energy, because wind energy has the main advantage like clean, renewable, and pretty flexible. So in our project, we particularly interested in offshore wind energy because offshore wind has a higher speed than on land, and it's quite stable due to the absence of barriers over the sea. And moreover, offshore wind turbines are larger so that they can generate more power. And in order to make better use of offshore wind energy, we need to predict wind field. We usually observe wind energy at a height of 100 to 200 meters of the atmosphere, and the airflow in this area is turbulent. Turbulence means chaos out of order. In order to predict the wind field, we must model turbulence well, since turbulence behaviors vary differently between stationary and non-stationary. So we need to determine whether it's stationary or non-stationary period. So we need to collect data before we can process and analyze them. You can see this picture shows the ocean horizontal area turbulence study. It's conducted at 3 kilometers south of Martha's Vineyard, Massachusetts, in 70 meters of water, under the RC interaction tower. So we can use this equipment to get data. You can see that there are 18 sonic anemometers at 5 and 5.58 meters in this horizontal array, and a standalone sonic anemometer at 9 meters. So total of 19 sonic anemometers are used to collect wind speed based on those 4 physical properties, UV, W, and T. And at this stage, the database is split into 515 4-hour periods and or UVW components in a rate of 20 Hertz. So current technology is only predictable to stationary conditions. So to find non-stationary transitions becomes the destination of my research. We apply a recent developed multi-sensor stationary analysis technique version 2 to OHAT dataset. And in order to from raw data to non-stationary period, I need those UVW components sampled using a total of 19 sonic anemometers at the frequency of 20 Hertz are collected from OHAT. Then I use Fortune program to check data availability. After that, I found 53 hours without missing data. So from 4 UTC October 17th to 8 UTC October 19th, 2004. Then I threw all the data during those 53 hours into MSAT-V2 to test whether a time series is stationary or not. This depends on the significance level of 0.05. It gives me the output, which confirms the non-stationary period. And this figure shows that the time series of 3 minutes averaged velocity components in each sonic instrument coordinate system during a 53 hours period. The gray shaded strips in each panel shows the non-stationary period intervals determined by applying MSAT-V2 with significance level of 0.05. So it shows that before 15 hours and after 15 hours are very different. We can see that in the U and the V components are most obvious difference. The difference shows that before 15 hours, U is positive, and after that, U is negative. So positive U means the wind is along the prevailing direction, and the negative U means the wind is against the prevailing direction. So when the wind changes from along the prevailing direction to the opposite direction, it's expected to the most non-stationary period. And this figure also shows that when you switch from positive to negative, MSAT-V2 will tell us that it is the most non-stationary period. And we can see the black slide line in each panel shows the data from the standalone sonic anemometer at 9 meters facing 205 degrees. And the other lines shows data from the other 18 sonic anemometers at 5 meters and 5.58 meters facing 255 degrees. So we can see the black one is different from the other colors. That's because that the 9 meter sonic anemometers and the other sonic anemometers points in different directions. So we recast velocity measured by the standard along sonic anemometer at 9 meters into the coordinate system of the sonic anemometer on the horizontal array. This figure shows time series of 3 minutes averaged velocity components. And then we can see 3 minutes average horizontal velocity components measured by sonic anemometer at various heights are similar to each other, such as 5 meters and 9 meters. And this project focusing on analyzing data, the results shows that MSAT-V2 determine non-stationary event when yield changes from positive to negative. That is consistent with our expectation. And meanwhile, the results also tell us the dependence of 3 minutes average horizontal velocity components on height is weak between 5 meters and 9 meters above the sea surface. So I hope the results of this project can make some contributions to offshore wind energy for rescating. Thank you so much. Any questions?
Questions?
Hi, Yanqiu.
Hi.
I may have missed this. I hope I didn't, but I wanted to ask: are there any like ecosystematic consequences to the wind farms?
Yeah, I think, in my opinion, yeah, is your question asked for to wind farm?
Yes, like is there any like danger associated to the ecosystems if a wind one wind turbine is nearby?
Yeah, I'm not really sure this answer, but in my opinion, I think it will have some risk. Yeah.
Okay, thank you.
Thank you.
I have a question about where the change in you see is this non-stationary change. Is it always associated? It seemed to be associated with the shift, kind of in the average quantity. You know, where it dropped suddenly, UV or W dropped, or it went up. Is that the reason for the non-stationary behavior, the shift in the average?
Yeah, so we can see this picture shows when you switch from positive to negative, it means the wind direction is changed. Yeah. So we always want wind from the ground of the turbulence, from the turbine, because we want to get the wind energy. However, if it changes to the from the back goes through the turbines, we will not get any wind energy. So if the wind direction changes, we determine this will be non-stationary period. Yes. Thank you.
Thank you.
Okay, thanks for that presentation. And now we're going to close out the symposium with Alisha Wellington, who is from my city of Philadelphia. She's a Penn State meteorology student, and she was also, she was mentored by Jerry and also XC. We actually had a very good team there, and we enjoyed talking to and working with Alisha. And Alisha, I know your mom is on, Miss Wellington. You got a young, bright genius there. So thanks for, you know, everything you've done. So Alisha, sorry to embarrass you, but.
Thank you. Thank you so much for the introduction. I'm going to go ahead and share my screen here. So hello everyone, my name is Alisha Wellington. I'm a student here at Penn State University where I study meteorology and atmospheric science. And today I'm going to be talking to you guys a bit about Hurricane Fred. We'll talk about the observations and the challenges of the forecast. So here in these images here is satellite imagery of Hurricane Fred. You can see the Cape Verde Islands and how massive that hurricane was. And it covered pretty much almost the entire set of islands here. So, and this shows without without the islands, but you can see how big this hurricane was here. So just a short introduction. Cape Verde is an island nation composed of about 10 islands located off the coast of West Africa. So it's in the central Atlantic Ocean. This island nation is home to 550 residents. And what really made Hurricane Fred really significant was it was the first hurricane to pass through Cape Verde in over 120 years. So this was a shock to a lot of the people here. And so even these images, you can see some of the destruction it left. There were 2 fishermen from Cape Verde that went missing and were later presumed dead. And 7 out of the 10 islands were damaged, and the damages were estimated to be well over $2 billion. And so the major problem that we face here is Cape Verde is considered a data void region where there's limited data and observations that we're getting from this island nation and from this region in this area because there are really not a lot of radars and not a lot of buoys. So we're not getting a ton of measurements. And so if we don't have a lot of measurements, that leads to us having these poor initial conditions, and you need to have really good initial conditions in order to have a good forecast. So it's just the setup goes poor measurements, poor initial conditions, and then a poor forecast. So the objective of this project was really to understand the errors associated with this forecast within this data void region. So just to talk a bit about the data set and methodology here. So I used various data sources, including satellite observation from UMetSat, reanalysis data from ECMWF, and most importantly, the last 2, the National Hurricane Center satellite-based observations, as well as simulations from WRF, the Weather Research and Forecast Model. And so all these sources I pretty much analyzed in MATLAB, and we use very important variables, including geopotential height, wind speed, pressure, and radiance, which we'll talk about a bit more. So just to follow up to that, the WRF simulation had a horizontal resolution outer domain of 15 kilometers and an inner domain of 3 kilometers, and it ran from the 29th of August to the 1st of September. And now to jump into the hurricane and some things associated with it, we'll talk a little bit about the synoptic timeline. And so this hurricane originated from the African easterly jet. You can sort of see here this motion of the winds here. And so there are a lot of disturbances. There can be tropical disturbances every few days in African easterly jet, but this particular disturbance formed into a tropical wave on the 29th, forming right off of the coast of West Africa. And it later fueled into a tropical depression as this low pressure center formed. And just a day later, we had even some warm water and wind shear that intensified this hurricane into the official development of a Category 1 hurricane. And so the hurricane, it remains over Cape Verde for the evening of the 31st, and just a day later is when it pretty much weakens and passed over Cape Verde. And so now we're going to talk a bit about the results that we've seen. So the first result we've seen came from the best track when comparing the National Hurricane Center's observations, best track from the observations, and then the forecast from the WRF. And you can see there's a discrepancy here and even where this best track began. The National Hurricane Center track began a bit north of the WRF track, and then the 2 tracks cross. But what's really important about this is here you can see there's some type of discrepancy here in where the WRF simulation thought that the hurricane would go. And what's even more important is this is the time period. Each point here is every 6 hours beginning the 30th of August. But here at 18Z on the 30th, you can see here, this starts this period where it was some type of discrepancy between where the hurricane was supposed to go. And what's important about this is this was a time where we needed to know what was really going to happen, because this is when it was intensifying, and this would be the time we really wanted to send out those preparation notices for the communities of people. Another important result we saw here was the discrepancy in the minimum pressure reported by National Hurricane Center and the WRF. There's about a 10 millibar difference. And what's even more important here is not only the difference in the value, but the strong drop off. You can see the National Hurricane Center reported this significant drop off here on the 31st of minimum pressure, while the WRF, it not only was delayed in the time that it said that there was going to be a drop in the minimum pressure, but also the magnitude that it decreased was slightly different or majorly different than National Hurricane Center. So that was something important to note because that hurricane center is really low. So the center of the actual hurricane. So we want to know what that pressure value looks like. And this result was actually the most surprising to me. The maximum wind, it was really different for the WRF and National Hurricane Center. Here, the WRF was about, the highest maximum wind was about 47.3 millibars, knots, while the National Hurricane Center went up to 75 knots here. And what's really, really important about this is here, if we follow just the WRF forecast, we wouldn't even classify this hurricane as a Category 1 because it's only reaching 47 knots. So you can see here, this discrepancy is really important. Also, you can see this sharp intensification and incline in wind that is given by the National Hurricane Center. So that's something also important that we wanted to point out and we saw here. And so next, this is something also important we saw was the brightness temperature deviation. So the brightness temperature generally tells us a bit about the convection associated with these hurricanes, as well as the cloud tops. And so here on the left, you can see this is the observation, the observed hurricane, and here's the WRF simulation. And not only do the values differ, but also the organization of how expansive this storm is. You can see it a bit better in this slide on the 31st at 0Z, where you can see how massive this hurricane is and how different even the eyewall region is when being compared to this WRF here. There's less organization, and essentially we're seeing colder cloud top temperatures here, and that's telling us a bit more about how intense these clouds are, and in return, how intense this hurricane is. So we're seeing the WRF simulation was pretty off in this area, and that's really important just from looking from the outside, because as I mentioned previously, this is still a data void region, so we want to be able to depend on these observations to get a bit more about what's happening, especially in this region where there's not a lot of measurements. And just to tie everything together, when comparing the WRF to observations, we had a minimum pressure observation that was 10 millibars lower than the WRF forecast. We had a maximum wind observed wind speed that was 27 knots higher than the WRF forecast. And we had the WRF forecast track ultimately deviate from the observed track. And lastly, we had the brightness temperature in the WRF being less organized, warmer temperatures, and suggesting a weaker convection and essentially a weaker hurricane. And so essentially we're seeing through all of these results, we're able to see how different the forecast was and pretty much why there were issues in preparing communities for what was happening because the forecast was so much off. And so just to bridge the gap here and what we want to do in the future. So we would take this result here of our brightness temperature, as you can recall, I mentioned how much these two pretty much differ. So in the future, what we want to do is we want to bridge the gap using data assimilation to combine the satellite radiance observations and the numerical model to essentially improve the forecast. So Cape Verde is still a data void region, but what we can do is we can use these observations to pretty much pull in what we observed and what we thought would happen and kind of bring those two together to have a more improved forecast. And so here are all my sources. And I just want to thank all my mentors and all my peers for an amazing summer. I also want to thank the National Science Foundation for funding this project as well. And I'll be happy to answer any questions.
All right. Thank you, Alisha. Time for one or two questions.
Alisha, so you showed that the track of the model was a bit different to the track that was observed, and you showed that the intensity was weaker. Do you think that having those tracks be different could have helped to make that difference in intensity?
Yes, definitely. Yes, I would definitely like agree with what you're saying pretty much. I think essentially WRF was not, the forecast didn't represent as strong as Hurricane Fred was. It was indicating more of a weaker storm. Even the timeline is off in the best track, so you can see it really didn't follow what exactly was happening here. But I think the WRF pretty much underestimated how powerful this storm was. The pressure was not as low as what really was observed, as well as the wind. It wasn't as high. I think the wind was really a strong indicator here, was extremely low here compared to what was really observed. So ultimately, I think WRF really underestimated this storm a bit and the intensity of it.
Thank you.
One last question.
Hi, Alisha. I also want to ask you a question. That is, when you are comparing WRF results to observational data, one thing is that the WRF results, for example, it represents a time average over your integration time step, perhaps like 5 minutes, I don't know. And it's also a spatial average within your grid. I wonder whether your observational data are kind of the same format, or your observational data are more like at one time snapshot and at one point. I just want to get like a little bit more information about that.
Sure. So I hope I understood correctly. So when comparing these two, the sort of model I follow was making sure I compared the same time. So although the resolutions might be a bit different, it was really important to make sure I compare the same time to kind of see what was going on. So for example, in the best track, each of these represented every 6 hours. And so more so the timing of the storm was compared. And so the observations were likely different, calculate different than the forecast, but more importantly, what we want to do here is just compare what kind of like a snapshot of what was happening at that time for each point, pretty much every 6 hours from the 30th to the 1st of September.
Okay, well, I'm going to kick it over to Ray because I want to stay out of his wrath. And Ying, we'll follow up with your question, but it was snapshots at every 6 hours. And she found the minimum and maximum, minimum pressure, maximum wind, and that's how she determined the track. Ray.
Yeah, I just want to wrap this up. Could start by thanking the students for their presentations. However you'd like to show your appreciation. They've been at this for, geez, I think exactly 2 months. You know, so I'm very impressed myself with their progress in only 2 months under the conditions of a pandemic. To me, it's nothing short of miraculous. So I'm very appreciative for all their hard work and devotion over the past 2 months. I also want to give a shout out to the National Science Foundation. I think I may have forgotten that in my introduction. This is our first year of a 5-year renewal grant, and they've been very cooperative and flexible in allowing us to run the program virtually. And I also want to thank the mentors who, you know, are kind of, I call them the heart of the REU. They're here year in, year out. Many have been mentoring for, you know, a half a dozen years or more within this program since its inception in 2013, started by Jose Fuentes. So I want to acknowledge their longstanding commitment.